OK, great. So I wanted to talk about, I'm supposed to talk about local to global stuff. So I guess the vast majority of this talk will take place on the spectral side. So somehow the idea is to, well, what's supposed to happen is there's supposed to be this extended spectral Whittaker category. And it's built out of quasi-coherent sheaves on G-check local systems. And this funny guy, there's some non-trivial glue.
Spectral, where does it come from? In number theory, we have the spectral side and geometric side of the trace formula.
Yeah, it's by analogy.
But this is Galois side.
Yeah, well, it's like spectrum of Hecke algebra or something like that. So somehow the idea is you want to decompose things into eigen things for the Hecke algebra. So, yeah, sorry. So somehow the idea is that you want to decompose stuff into eigen things for the Hecke algebra, and so this is where this is where, you know, this is what gives you the eigen value type things. But anyway, so let's call it the Galois side, if that's fine too. It's not terribly meaningful. So anyway, so the vast majority of this talk will take place on this side, although I will refer to things like G rather than G-check. Hopefully that's not too confusing. And also, so somehow the idea is going to be to try to give some version of the description of these two categories from purely local data on the curve. And gluing will be something else. So now I can erase this. So what's the idea behind doing all of these things? Well, to some extent, we've already seen what one wants to do. So we have our curve x. Whoa. And suppose we pick a point on x. So then we can consider this moduli stack of G local systems. And well, a point x gives us an evaluation map to BG. Namely, if you have a local system on a curve, and you've got a point on a curve, you get a G-torsor for every point. And well, they're connected by some kind of a flat connection. So there's this map. And so the upshot is, well, this gives you a way to construct quasi-coherent sheaves on local systems from quasi-coherent sheaves on BG. We already said that just by pulling back. So something very naive. We can take a sheaf on BG and get a sheaf on the local systems. All right, so well, let's recall that quasi-coherent sheaves on BG is just the representation category. It's just georepresentations. All right, so well, of course, there's no way to recover all of local systems from just this kind of data. But the idea is that you can vary the point, and you can take collections of points, and you can study how these things vary, how these functors vary as the points move and collide and things like that. So idea. Study such a functor over the Ron space. This is sort of what makes it local to global. We're starting with some version of representations of G, and we're ending up in local systems.
Why some version of representation?
What's that?
Why some version of representation?
Well, again, because we'll be working over the Ron space.
Oh, in this sense. Okay.
Yeah, just that. So, well, we already saw that we can build that starting with quasi-coherent sheaves on BG or rep G, because it's a symmetric monoidal category, we can build a factorization category. So we have the factorization category. corresponding to two representations of G. So for the purposes of this talk, because we're studying various functors between quasi-coherent sheaves, it will be extremely convenient to describe this category in geometric terms, as itself quasi-coherent sheaves on something. And we've already seen how to do that. So this is just quasi-coherent sheaves on the horizontal jets applied to BG. So rightly, I should write BG times x derived here, but let me not do that to save some notational, to save some room on the board. It will always be implied. So well, what we saw from Dennis's talk yesterday is that there's a map from the stack of local systems, more or less by definition of the jet space, G times the Ron space to this jet space. So these are all maybe sort of funny looking symbols, but at least for a fixed point in the Ron space, this is an extremely simple map. So a point in the Ron space is just a subset of X. And well, the target here over that point is just that many copies of BG, and we just evaluate our local system at each of those points. So let's just also call this the evaluation map. So we want to just, we're going to take quasi-coherent sheaves here and end up, with quasi-coherent sheaves on local systems. Well, so we want to integrate along the Ron space in order to be able to do that. So there's a projection map. And so
just horizontal is the rank version of jets, right?
yes. Yeah, so this lives, oh, well, oops, maybe, so maybe I should write Ron here. So this is a space that lives over the Ron space. And all of this is happening over the Ron space. So we have this localization functor from quasi-coherent sheaves on this just horizontal VG. Maybe Ron to quasi-coherent sheaves on the local systems of G. So this is just given by, well, first we pull back, and then we take the Durand push forward. So this is already the Durand stack, but I'm going to write Durand here to emphasize that really we're not just taking the quasi-coherent push forward. This is like the D-module push forward. All right, so this is, so we have such a functor, and then the main theorem here, which is due to Dennis and Jacob, is that, well, first of all, this localization functor admits a continuous, fully faithful so this is the key point, right adjoint which I'll call co-localization. So maybe the notation isn't so great, but well, once I started with the localization, that doesn't leave much choice. So from quasi-coherent sheaves on local systems to quasi-coherent sheaves on this jet space. Oh, well, explicitly we can describe what this right adjoint is just by, well, because both of these functors has a right adjoint, and so this is just given by first you pull back and then you push forward, and well, these are the yeah. Oh, sorry, which yesterday's theorem?
So there is a theorem that D-modules are G also fully.
So let me postpone your question. I will address that later in my talk. So, I mean, there is also such a theorem, and I'll say something more about it later. And so you might be asking how it's related to this one. Yeah, you will. Yeah, so that will happen later.
So the non-trivial part here is fully faithfulness, right?
Yes. So everything else is more or less trivial, but the theorem part of this theorem is the fully faithfulness statement.
Can you somehow say what underlies this theorem?
What's that?
Can you somehow say what sort of underlies?
So why? So
Why should we believe in this theorem?
why should we believe in this theorem? So,
I think, seriously, I think the answer would be the miracle. It's a miracle of science. In the sense that, like,
You know that
one way you might guess something like this is that there's a Betti version of this theorem, which we're not talking about, and I will not say anything about, but which works even better than this one. And so you might hope that there's an algebraic analog of that.
So you're saying that there's kind of topological analog to this theorem?
Yeah. So you might guess this kind. What's that?
okay, tell him. Just write the symbol for him.
I'm not sure which symbol you want me to write, but maybe we can postpone this discussion to the discussion session. So one thing that will happen then is that I'll sketch a proof of this theorem, actually. So, but I don't think that answered, but the proof will not answer the question of why you might think this is true, though.
Let's go on to have a discussion in the topological setting.
Yeah, okay, yeah. So, what's that? Oh, it's not directly related to the, so there was a statement about contractibility of the space of rational maps. This is not directly related to that. This is certainly related to the contractibility of the Ron space, which is itself, which is itself kind of a miracle. So. Yeah, but this is, I mean, this is a different sort of statement than that. I mean, that's an input to proving this kind of thing, but there's more to it than that, is all I'm saying. What's that? Yeah. So what's the? So certainly the pullback functor here is fully faithful, and this follows from the contractibility of the Ron space. So that's true, but this functor is, well, this functor is certainly not fully faithful. So anyhow, so.
Just a linguistic question. When you say that there is a fully faithful right adjoint, is there another right adjoint?
No. It's a statement that the right adjoint is fully faithful.
That's a linguistic.
Yeah. So, yeah. Yeah. I don't know. I mean.
You mean to say there is a right adjoint? The right adjoint is fully faithful.
I mean, if a right adjoint exists, it's unique. So so anything I say about one will be true of all of them.
It's a linguistic.
Yeah.
That's how to phrase it.
Okay. Well.
Faithful should be an end, but forget about it.
Well. Okay. I think. No, not quite. It's a little bit different than non-abelian punctor. It's related, but not exactly the same thing. Let me let's postpone that till the discussion, and we'll also see how this thing is proved. And the proof from one of the nice features about this proof of this theorem, by the way, is that it'll use everything we've learned about DG categories, and maybe a little bit more even. So it'll be, well, so you know, that stuff is all very abstract, but maybe this gives an example of what to try to understand this proof is a good way to learn about DG categories and all of the, you know, things like dualizable and tensor product of DG categories and things like that. Yeah. So P upper strict. So really, so P is a functor from local systems times the de Rham stack of the Ron space. So, well, nothing is happening on the local system. So I just mean the D-module pullback. Maybe I'll say de Rham. So the point is you get a. So the category that we're considering here is quasi-coherent sheaves on locals in the local system direction, and de Rham and D-modules in the Ron space direction. And this pullback functor is just, you know, it's constant along the Ron space. And you remember the structure of the D-module structure there. That's all I mean. Is that? All right. So I think that's all. For the time being, that's all I want to say about this thing. But now we'll now let's move on to the D-module version of this. So I want to replace quasi-coherent sheaves here by D-modules. Not here, certainly. But the idea.
Have we ever considered before D-modules on local systems?
No, we haven't, and we won't need to. What we will really need, so what we have considered, what came up in what Dima was describing in the discussion this morning, is some relative version of D-modules between local systems for a Borel. But this will be kind of the warm-up to that, because just to save on notation, I'll describe this version and then explain how it changes in the relative situation. So it's the thing that corresponds to the zero Whittaker coefficients on the other side. So what we'll want is a local description of D-mod of LocSys G. I guess another answer to this question is that there will be a similar local description for G bundles, and so that will come up in another talk. So well, what should be so then you can ask, well, what should be the local version of this story? And that's not, you might at first guess that just replace by D-modules, but that's really an unreasonable thing to do. So instead, we're going to define a local version of something called the local infinitesimal Hecke stack. And let me Hecke sub loc. So what this is going to be is, well, there's a natural map. So we have this. So we have this jets horizontal with BG. Oh, whoops! Before I do that, so I forgot to say something else. So the key point is that we're going to, rather than looking at the formal disk, so we can think about BG as G bundles on the G local systems on the formal disk. So recall BG as local systems, as G local systems on the, I don't know, it doesn't really matter whether it's which version of the formal disk you take. So we'll need to consider LocSys on the punctured disk. So this is not a sort of object we know how to define yet. Nothing anybody's said so far gives a definition of this object. So I want to emphasize that this is not the same as the meromorphic jets that Dennis defined yesterday. That's a reasonable construction for affine things, but not for something like local systems, not for something like BG. So I won't give a definition. That will happen in Dennis's talk on Friday. Friday? Yeah. Or
maybe we could do one of the tutorials of Q&As.
Yeah, if people are really impatient about it, we can do it in one of the Q&As, but we'll describe this on Friday. So I won't actually need very much about this other than its existence and some very, very mild formal properties. So there's obviously a natural map from BG to local systems on the formal disk, just the same restriction map. So you restrict your local system from the entire formal disk to the punctured disk. And so just as a bit of notation, for the purposes of this talk, what we'll really be interested in is the formal completion of the stack of local systems along this map. So this is the formal completion. What's that?
It's closed.
No. So no. So formal completion is an operation that makes sense for any map whatsoever. So it has another name, formal completion, which we'll see later, which is the relative de Rham space, or relative de Rham stack. But anyhow, so the upshot is that there's a version of this over the Ron space which forms a factorization space. There is this guy, a factorization space. So what we'll really be interested in is the thing I alluded to earlier, is this local infinitesimal Hecke stack. It's look. So by definition, it's just, well, there's an obvious map from BG to this guy, or from from the horizontal jets into BG, into this factorization space, and we can just take the fiber product of it with itself. So it's jets BG crossed over. This is all over the Ron space like this. So this is a funny looking formula, but all it says is something very simple. So it's, well, the reason it's also called I use the word Hecke is because, well, it's a stack that classifies the following data. So what does it classify? This thing? It actually doesn't matter. Oh. Well, okay, no, never mind. Let's pretend I didn't say that. So it classifies the following data. So one is two local systems. So systems. Maybe I'll say infinitesimally close. So that's extra piece of data. Local systems on the punctured disk, on the formal disk, and the second thing is identification. On punctured disk, so compatible with the infinitesimal identification. What's that? Of the two local systems, so of their restriction. So what's that? So this stack classify over a point x. Two. Yes. Infinitesimally closed means that, well, these are close. Oh, did I say closed?
Yes.
Oh, I apologize. Infinitesimally close.
Yes.
What does that mean?
Yes.
So, well, if you look at the stack of local systems, one way to describe it is that an S point of this is a local system on S times whatever you're classifying local systems. Two are infinitesimally close, or the data of identifying them infinitesimally is to give an identification of the restriction when you look at the reduced part of S. Identification. So
what does the whole sentence mean when you say classifies the following data?
So this is over, let's say, well.
So you say that if you want to describe as an S point
Uh-huh.
of this whole thing, then you need two S points with respect to local systems together with the identification of n on S reduced.
Yep.
And in addition, identification of S times the function.
Yeah.
And what does the hat mean?
The hat?
Yes.
Hat means formal completion along the diagonal here. Which is, what's that? And there's another hat here, yeah. You can get rid of some of those, but let me keep that explicit.
Sorry, and what does that hat mean?
Which one? This one?
The small thing.
This is the, so we consider,
Oh, I see, it's this one.
yeah.
Just what's this first one? Close.
Infinitesimally close?
Two infinitely close.
Local systems. Infinitesimally close. So that's actually a piece of data. So again, it's a pair of local systems, which means that for every S, it's a local system on S cross the disk, together with an isomorphism of the restrictions to S reduced cross the disk.
What's below?
Identification.
And below.
Oh, compatible with infinitesimal identification. So there was already an isomorphism on the reduced part, and you also want an isomorphism on the punctured disk. So you need the compatibility, so these isomorphisms have to agree when you restrict to both the punctured disk and the reduced part. So let's not. Oh boy.
This is restriction. It's mapped from BG to local systems. So I mean, I guess we haven't defined local systems on the punctured disk, so it's not really, the D hat doesn't map to the punctured disk, right?
No, but this is the same as, so one thing.
Same for the attic disk?
Yeah.
Okay. So it really is.
That says you have that local system and two identifications.
Sure, yeah. But
It's the same.
yes, but saying two local systems is a little bit more symmetric. And I like to keep the,
Two local systems and two identifications.
oh,
Identifications on S reduced and identification on.
that's right, but there's also an they also have to be compatible.
Yeah, of course.
Yes. So because we're in the infinity world, that's an identification of the identifications on the restriction. But yes. What's that? Yeah, so this is all happening over the Ron space. So I write the symbol D. We already have seen the version of the disk over the Ron space. It's all. Or if you're not happy with that, you can pick a point on the Ron space. And then this will be really the formal disk around that point. All right, so So it's this kind of object, and these guys that will play. So the upshot is we have a groupoid. Anyway, so because of how we constructed it, there are obviously two projection maps to local systems. Is there a question? Question?
Yeah, I mean, naively, we think that the local systems shouldn't be Hecke step because they can take direct process.
That's right, but in the derived sense there are. So one feature of derived algebraic geometry is that if you take, say, an ordinary variety, you know, affine space, the nicest variety you can imagine, that points still have automorphisms. Because you can compute the automorphism point as the fiber product of the point with itself over the thing. So for instance, if you take the affine line and do this, you get this funny derived group that we've already considered, which is the polynomial ring in one odd variable, the spectrum of that. So even though things look not stacky at all, points can still have automorphisms in the derived sense. And we're really making a lot of use of that, yeah.
Is it possible to say kind of explicitly what this looks like over a point?
Over a point?
I mean, this step.
Yeah, well, I mean, we haven't said what this guy looks like over a point. And,
But you can. No, it's your favorite guy.
yeah.
So it's, okay, so let's say it's 0.1g times 0.1g over Lie algebra direction.
Yeah.
Oh,
That's
sorry, it's his favorite guy.
Yeah, that's right.
It's that.
It's that.
Yeah.
Okay, and I know I don't know how we discussed this. You know, if you have something over a point, you know, what is it? Is there an explicit structure you need to put there to see that it actually lives over the round space?
No, that's more art than science. So
Yeah.
this here. So maybe can I comment this?
Yeah.
Here we're running into real trouble. So if you think so have point times point over the Lie algebra. What's this Lie algebra? If you think of it, it's like local system with connection of pole of order 1, kind of regular singularity thing.
Yeah.
And what you really like to do is to keep this regular singularity. Like you would like to kind of put it in families, and that's something you can't do. Like if you want to make the points move and collide, you actually have to consider all local systems, not just those with regular singularities, and that causes a lot of trouble. Like I would really wish to stay within a world where like nothing with irregular singularities appears, but it's impossible. Like as soon as you allow the collision, you kind of all hell breaks loose.
You tried really hard last week.
Yeah.
Okay.
So
Yeah.
that's the source of trouble.
But this is really the real reason why you can make this thing live over the round spaces is because you can local system with singularities. It doesn't matter which singularities now that you then make the points move around.
Yeah. So
Yeah.
because I can say the word formal disk, formal function disk, because of these words, and these words are factorizable, this is what allows this to do.
Yeah.
So that's why we had all this terrible discussion yesterday. So there's all these disks.
So could I ask,
Yeah.
if there wasn't a round space going on here,
Yeah.
would it just be the fiber product of BG with itself over something?
Yeah, so if you take a point, so there's a point on the Ron space which corresponds to a single point in X. So then this becomes BG, this becomes BG, and this becomes the thing that Dennis was just describing. It's equivalent to the point over the Lie algebra. And so it's just the derived fiber product of those things. So I guess one thing you can note from that description is that this thing is not very big. At least the classical part of it is not very big. But it's the derived part that we'll really be making use of. So So by the very nature of the construction, we have a groupoid this way. So, well, so let's think about what we've got here. So we said that this space of jets was some local avatar of local systems, and we wanted to study D-modules on local systems, or we wanted to describe D-modules on local systems. And well, from the crystalline point of view of the description of D-modules, you have that, well, what a crystal is a quasi-coherent sheaf where you identify the fibers at infinitesimally closed points. So let's compare and contrast this with this kind of Hecke situation, where, roughly speaking, well, so you're on the, well, this is a purely local thing, so you're on a disk. So this will correspond, as we'll see maybe, to further restricting. You pick a point on the Ron space, and you might say that you can look at quasi-coherent sheaves which are identified at infinitesimally closed points, but where any kind of movement can only happen at those fixed points that you've picked on the curve. Anyway, so this is somehow the idea of why this and if you integrate over all possible configurations of points, then you should recover the infinitesimal groupoid. This is somehow the idea behind this, and I'll try to make this a little bit more explicit a little bit later. But so let's define the category. So we have these two projection maps. We have this groupoid. So we can consider the following category. We can consider quasi-coherent sheaves in this jet sky. Which are equivariant with respect to this Hecke stack. So an important remark is that I need them to be equivariant with respect to the Schrick pullback rather than the star pullback. So one instance where working with right D-modules is much better than working with left D-modules. So you might ask, so we only define Schrick pullback on incoherent sheaves rather than quasi-coherent sheaves. But that's no problem because, well, both of these maps are particularly nice. They're quasi-smooth maps, so there's actually no problem. So there's actually a quasi-coherent version of the Schrick pullback functor, which you can recover from the incoherent one. So this makes sense.
Just to get some sense of this, what is the typical fiber of this map?
A fiber of which map?
P1, P2.
P1 or P2? Well, so let's pick one. It doesn't really matter. So you've picked a.
Again, over a point, right?
Yeah. Let's do it over a point. So over. We can kind of compute this explicitly. So we have this guy is BG. This guy is some. Well, so we pick some G-local system, let's say the trivial one, and then we're supposed to specify another G-local system, which is infinitesimally close to it, and together with an isomorphism on the punctured disk. So this is something like so the reduced part of that will just be point, and so the only remaining structure is what essentially is what the tangent space of this is, and the tangent space will be. It's like the de Rham cohomology over the formal punctured disk.
Well, this is if you believe that this thing is smooth.
But you
Yeah. Yeah, that's right. But I mean, this is going to recover G shifted by one.
How do you know that this thing is smooth?
Which thing is smooth?
I mean, you said that these maps are quasi-smooth, so somehow that's what I'm trying to.
Well, so checking that something is quasi-smooth is pretty easy in these kinds of situations because I gave a modular description of all of these things. So quasi-smooth is a condition on the tangent space. Yeah. And so when you give a modular description of something, especially in derived algebraic geometry, it's very easy to compute. It's extremely computable, the tangent complex. So you just do this kind of computation that I was suggesting, that the tangent complex will be the de Rham cohomology of, it's going to be the fiber of the de Rham cohomologies of G over the formal punctured disk, which is over a point. You see that it's just G shifted by 1. So question?
Nick?
Yeah.
Yeah, you said something about the star pullback, so you need a star version in quasi-coherent.
No. So quasi-coherent sheaves come with star pullback,
Yeah.
and int-coherent sheaves come with Schrick pullback.
Sorry, Schrick, I wanted to.
Yeah.
Schrick. And you said that this is better to work in coh here.
What? No. We're working with quasi-coh,
Yeah.
but we're defining the Schrick pullback.
And for that you need the maps to be nice.
And for that, you need the maps to be nice. So in this case, you can imagine. So in this case, these maps are sort of formally proper, whatever that means, or well, they behave like proper maps. So you can define the Schrick pullback to be the adjoint functor, to be the right adjoint of the push forward. And the fact that this map is quasi-smooth guarantees that that's a well-behaved functor. For instance, that it's continuous and behaves reasonably well with base change, things like this. All right. So now, what time did I start, by the way?
We started 10 minutes past 10.
So I have 20 minutes. OK, no problem. So let me formulate the theorem.
Sorry, what's equivalent?
What's equivariant?
What do you mean?
Well, if you have a groupoid acting on something, you can consider equivariant sheaves.
With respect to what? I mean, let's go.
What's that?
I mean, you have.
So roughly
speaking.
speaking,
By constant law,
what's that? So just purely formally, here's a groupoid. So what does it mean to be equivariant? Well, it means I have a quasi-coherent sheaf here. I take the two pullbacks. I'm supposed to give you an isomorphism, and then this keeps going. There's a whole bunch of coherence data that I'm suppressing, and it's this kind of structure. So the theorem is that there's a fully faithful, localization functor let me call it crystalline localization from this category, from this Hecke equivariant oh boy, running out of room, to D modules on the local systems. Who's right adjoint, I guess. Is continuous and fully faithful.
what's the second script or what?
What's that?
Second line.
This line?
Beginning. No, second from the top.
What's the name of the file?
Oh, Chris, for crystalline, whose right adjoint is continuous and fully faithful. So again, it's the fully, well, actually now, both statements are not completely trivial. So I guess what I will try to describe for most of the remainder of the talk is a construction of this functor. And then the fully faithfulness will actually follow from the theorem about quasi-coherent sheaves and some other statement. But maybe before I do that, let me describe the relative version, which is actually the one needed for geometric Langlands. So there are a few modifications. So suppose we have a subgroup P, a subgroup of G.
Nick?
Yeah.
Interrupt you. Can you say please again, why do you want the D-module version of the quasi-coh version and the localization?
Oh, so yeah.
Sorry for interrupting. So Dima suggests to actually postpone the relative version
To the discussion?
time.
Okay.
because Just,
Okay, great. Yeah, I think that's a good idea. Yeah.
so
Okay.
Maybe we can even. So I think there were questions being asked now. Let's declare the end of lecture and then let people chance to ask a few questions now, then have a break and ask more questions and discuss this stuff.
Oh, there was something. So I still have some time, I think, and there were some other things I wanted to say, or which and well,
Relative and non-relative?
no, non-relative. So I wanted to say something about how to construct this functor, and I wanted to relate it to the other statement about the Grassmannian, which I promised to do anyway.
What do you say?
So I agree that maybe a relative version we should postpone. But do you? How does that sound?
I just think that I would need some time just to stare at this and somehow just parse what's written on the board.
Okay. I mean, we can do that also.
Let's maybe have a 10 minutes break.
Okay.
So if
Maybe you can say just sort of why we're doing this.
Yes.
Where are we heading?
Where are we heading?
Locally.
No, so locally where we're heading is, well, so at the beginning of this talk,
Sorry?
let me just write.
But somehow, I mean, you have formative theorems, and the question is, for example,
No, so yeah, so
approximately how this theorem will be used in full.
yeah, sure. So, well, so now there are two theorems that I formulated, and so let me try to explain how that fits in with the story that Dima was describing this morning, which is that, well, again, we're working completely. So far, we're only working on the Galois side of things. And so on the Galois side of things, we care about this category of int-coherent sheaves with nilpotent support. So we have this category. Now I'm going to switch to G-check because. So so this is the question that I'm answering. So the theorem I formulated the first theorem I formulated gives you a piece of this, which is quasi-coherent sheaves.
Oh yes,
So that's a subcategory here.
but how is it related to the theorem you formulated?
The theorem I formulated gave a local to global version of this category. The first one,
Partly, right?
Yes, that there was a fully faithful embedding.
Fully faithful function.
That's right. So as Dima explained, this whole strategy is going to be to construct some local categories, and on both sides there will be a fully faithful functor, and then to compare the local categories will be equivalent, and then you want to compare the essential image. Okay. But this category doesn't really have a very nice local avatar, and instead. The idea is to split this up into two categories. One of them is just quasi-coherent sheaves, and sort of the rest. And the rest has to do with the fact that this relative thing that I didn't quite describe, which is that you look at parabolics, and then very roughly speaking, you look at quasi-coherent sheaves with a flat on the parabolics with a flat connection along G, and it's to describe those category. So
G.
Yeah. So there's. So if P check inside G check, you have a. So you can consider quasi-coherent sheaves here with a connection along here. So the point of describing D-modules here is is because formally the answer will be very similar to the answer for this one, and fewer symbols are involved.
When you write Hecke algebra, you mean like G by invariant Hecke algebra?
Yes.
And so the point is that what you want to say is that all of these will be kind of local, or will
Yeah.
have a local description.
That's right.
And on this sort of spectral, on the other side, this will be something like images of Einstein theories.
Yeah.
This piece of the category. I mean, what Nick is saying is that he kind of breaks up this in category according to different parabolas. And so the piece corresponding sort of to given parabolic, eventually on the other side will have something to do with this series.
Yes.
But correctly defined as
Just a second. Yes, please.
So the point is that even within the spectral side, it's not that this category is literally cut into two pieces. So for example, this quasi-coherent does not behave as an open piece layer.
Right.
Unlike the geometric side where the non-zero length is the open condition. So what will happen instead is that already on a single spectral side, the category is actually only embedded into the GUI.
yes.
So in this sense, it's unnatural to expect that that Eisenstein series, that the part that we are adding up to it is not going to be Eisenstein series, because Eisenstein series is actually a subcategory. It's supposed to be a subcategory. So its image in there can be thought of as Eisenstein series. But the category itself, I mean, it's some data.
Oh, yeah, I see. So it's a category, then there will be a functor into the category we want, but it won't be fully faithful. Is that what you're saying? Well, is there a functor from this category to this?
I'm sorry, I just...
From
is there a functor from this category of LocSys, check, you know,
there's a
connection
functor from
to the category, no,
To this one?
category,
there's a functor
Yeah.
from the... Yes,
Just
there's a
restrict
functor,
and
but
forget.
It's not the one that you should be looking at.
Yeah.
There is a functor from the top line
Yes.
to the gluing of the two category downstairs. The two categories are the quasi-coherent and this category of relative quasi-coherent with relative connection along
And
this
what does
line.
the word mean?
It has a precise meaning. There's a
Well-
way to glue two categories. So to get
Think about if you have sheaves on a closed and an open,
Okay.
the usual kind of devisage.
And that will be discussed in my talk tomorrow.
Sorry, just
Uh-huh.
a question. So you said about this expression relative connection.
Yeah.
So you have x mapping to y.
Uh-huh.
X is LocSys check and
Yeah.
y is LocSys check. And then you're talking about quasi-coherent shifts in x with connections along y. That's not something I used to, I guess.
No, the opposite. Quasi. Oh.
But that's how you said it.
Sorry. Let me just. So, let me just give a more formal statement. So you have a map from x to y. So this will not be. So what I will say is close to, but not exactly the category that's relevant here. But it will give precise meaning to what I said. So things with connection on x are sheaves on x duram. So this naturally maps to y duram. Sorry, I think you're pointing out that I misspoke. But what I really want is this guy, is sheaves on this guy, which are things with a connection along with the fibers.
Along the fibers, huh?
Yeah, that's right. Sorry, yeah.
Okay.
It's kind of infinitesimal to some degree.
That's right, exactly. Yeah, so it's literally it's sheaves on this guy.
Okay.
Although, again, so see, in the relative situation, there are two things. So for the Duram stack, we said that quasi-coherent sheaves and incoherent sheaves were the same. This was the equivalence between left and right crystals. On the other hand, in this relative situation, in general, they're not. And so there are kind of two versions of this that you can consider. And the one relative for this one, the relevant for this one, is some intermediate version. That, well, I can say or not, depending on what. OK. It will certainly appear in Sam's talk. So what's the plan now?
So maybe let's have a short break.
OK.